Hi, I am Mainak, and this is the introduction to our final year project on design and analysis of wearable microstrip antenna for multiband wireless applications. So what is microstrip patch antenna? A microstrip patch antenna is a metallic strip or patch mounted on a dielectric layer over a ground plane. That is a three-layered structure with patch at the top and substrate in the middle and ground at the bottom. Along with that, we have different types of feeding option to the microstrip patch antenna like microstrip feed, coaxial feed, aperture coupled feed, proximity coupled feed. In this final year project, we have used coaxial feed for feeding our microstrip patch antenna. Applications of microstrip patch antenna are in wide ranges of domains, like in mobile and satellite communication, in GPS, in radio frequency identifications, WiMAX radar, etc. Defective ground structure or DGS is a type of defect that we introduce in a microstrip patch antenna which helps in compactness of the antenna size, improving the gain, enhancing the bandwidth, and reducing mutual coupling. Now we will talk about our first part of the project, that is the rectangular microstrip patch antenna without DGS and with DGS. Here we have selected the patch size to be 21.5 mm to 25.3 mm. The dielectric constant selected is of 1.6. Feed point is at 6.0. Frequency of resonance is at 5.2 GHz. Next, in the DGS, we have selected two types of DGS, that is U and I-shaped DGS. The resonance we get through this improvement is at three different bands, that is at 2.3, 5.2 and 8.6 GHz, and hence we can use this defective ground structure improved version of MSA for multiband applications. Here we are comparing the return loss versus frequency of two different types of RMSA, that is without DGS and with DGS. We can clearly see the improvement in case of with DGS structure. Here we are achieving three different bands, and hence we can use that for different applications. Next, this is the comparison of gain versus frequency for the two types of RMSM. Here we can see there is a trade-off between the gain and the number of bands we achieve. Since earlier the gain was 8.09 dB and now the gain has reduced to 1.2 at 2.3 GHz, 6.0 at 5.28 GHz, 5.86 at 8.64 GHz. So we can see there is a reduction in the gain, but since these are above the 0 dB, we can still use this for different applications. Next, Agniv will guide you through the circular microstrip patch antenna, which is the next part of our project.
Hello everyone, I am Agniv Basu and I'm going to tell you a little about the circular microstrip patch antenna, which is also abbreviated as CMSA. So as you might have guessed by looking at this slide, that here it is just like the RMSA that Mainak has talked about before, just that here the shape of the patch is circular. Otherwise, it's just like a microstrip patch antenna. It contains a patch in a ground plane which is separated by a substrate of the dielectric as shown. And here we have taken the value of the dielectric to be 1.6 as we are dealing with wearable applications and 1.6 corresponds to a wearable material. So now we move on to the design of our proposed CMSA. So first we designed the CMSA without the DGS, and earlier we have seen that the RMSA was initially designed to resonate at 5.2 GHz, which is in the WLAN band. So while designing the CMSA, the idea was to keep the area of the circular patch roughly the same as the rectangular patch. Here you can see that AE and epsilon naught E are the effective radius and the effective dielectric constant of the CMSA. So using the equation displayed on screen, we have found out that the radius of the patch should be about 1.316 centimeter, and the ground plane, like earlier, is 40 millimeter into 42 millimeter, and the coaxial feed is finally applied at the location 6.225, 3. So as we can see, by doing all of these, the graph shown on the screen shows that the return loss is maximum at about 5.19 GHz, which is approximately 5.2 GHz, and the bandwidth is 185 MHz. And as we can see, the gain at 5.2 GHz is 7.98 dBi, which is also a preferable value. After this, we have introduced two defective ground structures, or DGS. One is in the shape of a swastika, as you can see, and the other is an X. The DGSs make sure that the antenna resonates at multibands, as we are dealing with multiband wearable antenna applications. So when we observe the return loss pattern as shown on screen, we see that the bands are obtained with resonant frequencies at 3.95 GHz, 4.34 GHz and 6.32 GHz respectively, with appreciable return losses. We observe in the gain versus frequency graph that the resonant frequencies of 3.95, 4.34 and 6.32 GHz is well above 3 dB, which is a preferable value. So this is all about the CMSA, and that's all for the introduction. Now Mainak will guide you through the software designing process using Zealand IE3D.